floor is yours.
Okay, great. Yeah, thank you for the very extensive introduction. I have like various topics prepared to talk about, but please feel free to interrupt me anytime if you have any questions. So I'll mainly gonna go over what is kind of machine translation today, what machine translation means for translators today, and then I'll see what other topics I still have time for. But that's kind of the most important things I wanted to go over. So as just mentioned, I've been working on machine translation for quite a while. So I'll come with some ancient history first. So this is actually one of the textbooks I just mentioned. So in statistical machine translation, we made a very clear distinction between a translation model and a language model. So there was the fundamental equation of statistical machine translation was reformulating the probability of an English sentence given a foreign sentence into the translation probability the other way direction. So probability of the foreign sentence given an English sentence multiplied with the probability of the English sentence. So this introduced both a translation model and a language model, and that kind of encapsulates very nicely what you want from a translation. So a translation has to be correct in meaning. So the meanings should be the same of the source sentence and the target sentence. That's what the translation model is doing. But then also the output should be fluid. And that's what the language model does. And it really depends on the kind of material you want to translate, where one might be more important than the other. So in these models, it was also possible to weigh the language model over the translation model. So if you think about literary translation, it's more important that things sound fluent and nice to read, and kind of there's a coherent emotional kind of story there. So there the language model is more important, but when you compare it to like legal documents, they don't have to read that nicely, but they should be absolutely have the right nuance. So even like in this place, the might actually change the meaning in a slight way that actually is then giving a different interpretation. So that's the two components that we had in statistical machine translation. So this was kind of the approach we used until about 10 years ago, maybe less than 10 years ago. The big breakthrough or turning point, or the most recent turning point, was 2016, when the whole field moved to neural machine translation. So this is just kind of a sketch of one of the early models where you kind of predict one word at a time based on the previous words we have seen. So these were kind of the models that were used then. So the interesting thing back then was they were only basically training a translation model. So they were only trained on data that we call parallel data that kind of maps source sentences to target sentences word by word. Here's a very influential chart I had in one of my papers a while ago that compared on the x-axis how much training data you have to train either a phrase-based statistical machine translation model or a neural machine translation model. So the green curve is a neural machine translation model, and both of the blue curves are the statistical machine translation models. And what everybody was surprised by, and what stunned me also when I discovered this, was the much steeper curve for the neural machine translation model, so that they're really bad if you don't have much training data. So the middle of the chart, 10 to the power 7, that means 10 million words of training data. Even at that point, you do better with phrase-based statistical machine translation models. But that green curve with the neural machine translation, the more data you have, the more it can take advantage of that. And that is a much steeper curve than even when it comes to this. I think ends up at around 500 million words of training data. So that was kind of the main thing that kind of stuck in your mind when you looked at this. The reason why there are two blue curves is because the neural machine translation model was, as I just mentioned, only trained on parallel text, so it was only trained on translated text. While in phrase-based statistical machine translation model, it was very common to have this separate language model that was trained on much, much more data. So the language model just had to be trained on output language text. So you can, any text in that language you can throw in, and you can basically build gigantic language models for that. So the dark blue curve that is a little bit higher than the light blue curve is how you typically would train these models. But to be fair to the neural model, to kind of train on the same data, the light blue curve is basically the more fairer comparison, because that is trained on the same amount of data. So this was kind of back in 8 years ago, where kind of the move happened to neural machine translation. And clearly, you know, the impression was you should also train these models on lots and lots of monolingual text, not just parallel text. But somehow this kind of, yeah, I wouldn't say it got forgotten, but it was never really very successfully carried out. So the neural machine translation models up till very recently were just trained on vast amounts of parallel text, but very little monolingual text. Just a few technical comments about how the models are currently being trained. So this is now the attention models and the transformer model. So this is the model that was proposed also around 6-7 years ago for machine translation. And it basically, the key idea here is that you have this attention mechanism. So you have to think about, if you go over the input sentence, it has a lot of ambiguous words, and you have to figure out what the meaning of these words are. And some words might be ambiguous. So the typical example people like to cite is the word bat, which might be either a baseball bat, or it might be that flying animal. A baseball bat is like, you know, an instrument to hit a ball, while the bat, the flying animal, is more like a bird. So how do you know what the word bat means? If you just come across the word bat, how does a computer know what it is? It has to look the same thing that we do. We have to look at the context, the surrounding words, and that's what the attention mechanism does. So it looks at the surrounding words and basically finds out, okay, there's the word baseball and ballpark and hitter, and all these words are around. So therefore, the meaning of the word bat in this sentence is probably the baseball meaning and not the animal meaning. And that's what the attention mechanism was. It's basically when it tries to figure out, can I refine the meaning of a word? Let's look at the surrounding words. Which words should I pay attention to get a better sense of what this word means? And then that gets pulled together, kind of get a refined representation of the word. Okay, so what I just described was actually the attention mechanism in the encoder, where you try to find the meaning of the word. You have the same, obviously, in the, yeah, I should have presented them the other way around. So you have the same thing when you produce the translation. So when you produce the translation, you also have to have some kind of attention mechanism, because whenever you produce an output word, there's certain words in the input that matter more than others. So if I start the sentence with "the house is," and then you basically have to look at the input sentence, which of the words in the input sentence matters most for producing the next word. So that's where the attention mechanism comes from. And the transformer paper was basically putting the attention mechanism not just in the kind of figuring out what the input words matter for producing the output words, but how to disambiguate the meaning of input words. So these are kind of currently the most successful models. They were then also used for language models. So when you now hear ChatGPT, that's where language models come in again. So language models are just trained on monolingual text, and they initially also adopted these transformer models. At the beginning, this seems to be a bit like the wrong model for it, because it was always mapping an input sequence to an output sequence, because that's what we do in translation. We have an input sequence in language, we produce an output sequence in another language, and that's what we have to do. And if you just do a language model, they just try to predict the next word in a sentence. You don't really have an input and output. So they kind of came up with this idea of just masking out some input words and then predicting them in context. But the way they currently are being built is just basically taking part of that model where you just try to predict the next word given the previous words. So these are called decoder-only models. And that name really only makes sense if you just follow the whole history that I went over, where in machine translation, we kind of view that as a decoding problem where the foreign sentence is encoded in some cryptic signals, and then it needs to be decoded. So you have an encoder that tries to find the representation of the words, and then a decoder that tries to predict the output words. So if you go away with the encoder, because you actually don't have an input sequence you have to encode, you just have to predict one word at a time, you're left with a coder-only model. So what has happened now more recently? People built gigantic large language models. So this is a slide actually already from last year, 2013, where the size of the bubbles kind of indicate how big the models are. So the biggest bubbles here are 500 billion parameters. So these are the number of kind of weights you have to learn during training. The good news is they didn't really get much bigger than that, but this is still a massive size of models. So that's what these language models today are trained on basically massive amounts of data and require massive amounts of models. To put in comparison, I put the text that the transformer model that was originally proposed for machine translation, and the big version of it had only 200 million parameters. So today's large language models are 1,000 times bigger than the translation models that kind of originated the whole idea of transformer models, and they were trained years ago. So the main benefit of these large models is they can just basically memorize and learn much more about more language, how language is well formed and how to express it well than our transformer models could. And that's kind of what seems to be needed to get any kind of benefit out of the monolingual data that they're trained on. Okay, so a bit of a review of when I said like we forgot about the language model in machine translation when we moved to neural machine translation. So this is some kind of ancient history. This is still statistical machine translation days. We actually used very large language models. So 126 billion token language model was used in a machine translation model. This is more than 10 years ago. These kind of data sizes were just really reached again with the large language models of today, like a year ago or 2 years ago. So bringing this to neural machine translation, well, the idea was kind of the same that we had in statistical MTs. We have a translation model that we now train with neural machine translation technology, and we have a language model that we can also train with neural machine translation technology. But we kind of merge them then and can combine the predictions. However, this was not really very successful. The most successful application of using monolingual data to improve machine translation was to kind of treat it as parallel data where the source site is missing. So you basically want to have a lot of monolingual text evaluators want to figure out what sounds fluent in the target language. You need to produce text that is fluent in the target language. So you want to have a lot of genuine text in the target language. So, but if you just take regular text in the target language, what is clearly missing is the original source site, so the foreign side of that sentence pair. But you could just train a machine translation system that translates in the opposite direction and then synthesize the source. So this is the idea of back translation, which is a very, very common idea. But the amount of data that was used for this, it was much, much smaller than the amount of data that is currently used to train large language models. It's typically just maybe a few times bigger than the amount of parallel data that was being used. Another idea was to kind of pre-train the models on monolingual text first. So that was pretty popular. This is actually very similar to what large language models do nowadays. But as I said, none of these use data at the scale that was previously used in statistical machine translation. And it really took large language models a long time to kind of get to those kind of data sizes. So the big topic right now, so I said there was a very important shift in machine translation almost 10 years ago from statistical machine translation to neural machine translation. And we seem to be in the middle of another big shift where we're shifting from machine translation to using large language models instead. So now the default is not, I have a sentence that I need to translate, I go to Google Translate. Now the default seems to be, I have a sentence that I need to translate, I go to ChatGPT. So where are we with that? A bit of a history for that too. So large language models, as I said, came out of, taking the transformer model from machine translation and just training a monolingual text. And mainly, it was mostly done to kind of learn kind of good representations for text, and then ultimately you did some other task afterwards. You did like sentiment classification or question answering or trying to match sentences in different contexts. The kind of seminal paper was this paper from GPT-2 that said language models are unsupervised multitask learners. So the idea was that we can just train a lot of these models on lots and lots of text and then turn any problem you want to do. It might be summarize a document, answering a question, giving a previous document, doing some kind of logical inference or maybe even machine translation, and just turn it into a text sequence. So this might sound today a bit obvious because that's what everybody's doing when they use ChatGPT, but it was kind of revolutionary 5 years ago that would actually work. And it did work relatively well. It was bad for machine translation because the models that this was tried on was trained mostly on English. That's still a bit of a problem today that the models that we have are mostly trained on English. And so this one was not very good at translation. Google's Palm model, when that came out, people tried to figure out how well can it do machine translation, and it was also pretty decent. And it was not as good as the state of the art. It was also kind of seen that it's important how to ask the language model how to do translation. So the idea of that you have to give it some examples. So it's called multi-shot prompting is important. And there is some kind of suspicion that also these models are just trying to monolingual text by kind of giving multi-shot examples that can do translation. So when ChatGPT came out, and Microsoft also looked at how well it can do machine translation. Again, it was decent, but below the state of the art. So the one surprising thing for people who worked on machine translation for a long time was that these models are not particularly trained on machine translation. They're trained on just, generating text in a language, mostly even English. So you just give it a lot of English text, and then they kind of produce translations. How do they do this? Is this a kind of an emergent behavior? So this is one of the big questions right now with the large language models, that there are all these claims that, oh, they can do all these things and they're not even trained for them. I can kind of come up with a new task for them to do and somehow magically they can do them. How is it even possible to these kind of gain some kind of higher levels of intelligence somehow? So one of the most interesting papers from last year was this study here that basically checked, is that actually true? When we say these language models are just trained on monolingual text, is that actually true? And they looked at the training data for Palm. So this is a study from Google. So they looked at Google's training data for their own language model, and they found out that in the training data that is supposedly just monolingual text straight from the internet, there are actually 30 million translation pairs, or sentence pairs with translations in at least 44 languages. I mean, it's always a bit hard to check that. So the way they did it is they went over all the documents that the model was trained on and looked at run language ID over the documents, figure out which sentences in the document are in which language, and then found documents that are in multiple languages, and then did some further analysis to check if these are translations of each other. If you actually carefully remove all this parallel data from training, so if you remove all the translation pairs from the training data of the large language model, then you get much, much, much worse translation performance. So it doesn't really learn how to translate kind of by magically matching up the languages. and discovering the translation task, it is really trained on translation data. So it is really good at large language models are really good at machine translation because they're also trained on the task of machine translation, because that's a big part of the training data. A little bit further detail here. So if you actually take the parallel data that is in the training data for PaLM and distill it out and really produce it as kind of parallel data that then typical neural machine translation model can train on, you can actually get pretty good translation performance on it. Okay, but at this point, why are we kind of just hoping that the large language model magically discover how to do translation? We can actually do what is typically done, which is... Is there a question?
No. Just someone forgot to mute himself. Just go ahead.
Okay, yeah. If anybody has a question anytime, I'm happy to.
Yeah, go ahead.
Okay, so I said what I just presented was just basically people just, the large language models came on, they were just trained on monolingual text, supposedly, but apparently that's not true. There was a lot of translated text in there. And they just said, oh, wow, it's doing so well at translation. But all this, like, why do we kind of hope accidentally these models learn how to translate? Why don't we teach them how to translate? And the way this is done is the same way this is done for all the other tasks that we want large language models to do. So we basically teach large language models to do various tasks, to solve kind of, summarize text, create stories, answer questions, do logic puzzles, all these things all these tasks that models are trained for, answer scientific questions, answer law questions. All these tasks large language models are trained for, so we can also train them to do translation. So we basically just create text that looks like this, which is kind of like how you would phrase, a particular task. So translate the following sentence from German to English, and then you give it the German sentence, and then you produce English, and at training time you give it the answer. So this house is groß, translate as the house is big. And at test time you would just kind of give everything up to this here and hope that the model would produce the translation from there. So we basically just use this as instruction data to fine-tune large language models. So we have done some work on that last year, where we kind of used a method called QLoRa to adapt models and show that this is pretty successful. I mean, last year was kind of the year where people started doing this more seriously. I want to highlight two more recent papers from this year where people did this, basically took large language models and adapted them for the task of machine translation. So this is here a paper by a PhD student of ours here at Hopkins, who did this mostly as a kind of internship project at Microsoft, where he showed that you don't really need that much parallel data, but you need also a lot of monolingual data in the languages involved. So if you wanted to do, English Arabic machine translation, you also have to present it with a lot of Arabic text, so it actually is more familiar with Arabic text. So you first fine-tune a lot of monolingual data for the languages involved, and then you fine-tune in a second stage on the parallel data. And in this paper, it kind of made the point that you might not need that much parallel data. So only like a few thousand sentences here. This is what is meant here by the WMT development says. So these are kind of high quality translations that are created by human translators and carefully vetted, but it's only in the order of 10,000 of sentence pairs. And doing this on Llama 2, which is like an open source model, at least us academics can fine tune fairly easily. You could actually get better performance than GPT 3.5. The other thing I wanted to highlight was the effort here from Anbabo. That's a company in Portugal that it's mainly a translation company. So they've put in a very serious effort of adapting Llama 2 to do the task of translation, because internally they actually want to have a good translation model. And they did this by, getting a lot of monolingual data on the language pairs they covered. They covered about like a dozen language pairs, mostly European languages. And then really all the parallel data they could get their hands on, but also filtered the data carefully one thing, for instance, we learned over the years that noisy parallel data is actually pretty harmful, so they could very carefully filter the data, so they only very clean parallel data. And then created and mixed that, created instruction data out of it, but then also mixed it with instruction data for other tasks, typical language model tasks like answering scientific questions or doing kind of some logical reasoning. And that model is actually publicly released, and you can actually try it out and see how well it works to kind of give you some sense of what it currently takes to train these models. So they train a model with 7 billion parameters. So that's kind of what you can run on reasonable hardware with a few tricks. The training for that took 80 GPU days. So this was the kind of monolingual parallel data training, and then the instruction fine-tuning took 8 GPU days. So on A100, so unfortunately these are quite expensive GPUs. They cost about $10,000 a piece. But kind of ballpark, you can see that this is something like, at least we at our university, if you would really wanted to and reserve the GPUs for it, we could pull this off. Okay, here's absolutely brand new results from last month. So this is the WMT competition. So this is a competition we set up every year, where I've been doing it for 20 years, where we mainly try to target researchers who build machine translation systems to kind of have an open forum to see how well good the machine translation system is. It's mainly targeted as academic institutions that kind of want to basically see if their system they're building is better than everybody else's. Mainly not so much kind of to figure out who's the best, but mainly to kind of establish that there's new methods. For instance, when neural machine translation came out and it did really well in these competitions, everybody just, had enough evidence to take that seriously, and then the whole field switched very quickly to new methods. So it's kind of a good forum to validate what actually works today. So instead of everybody writing their own papers and saying their stuff is better than everybody else's, this is kind of a fair test. So it's on a previously unseen 2,000 or 3,000 sentences that need to be translated, that were manually translated specifically for this purpose. So it's a completely blind test set that's not part of anybody's training data. And then it could be really seen as a test. Okay, so where are we here with the results? So this is for various language pairs. It's all English out of English into other languages, except we check Ukrainian at the end. So the good news is the humans still do pretty well. So why would a machine ever be better than a human on these tasks? So this is actually evaluated by humans afterwards. And the reason for that is mostly, if you kind of go to a translation agency and say, can you translate these 3,000 sentences, you're never quite sure how much effort they put into it. So even professional translators, if they just get paid per word, they might just, get sloppy and then produce, quick and dirty translations. And apparently for English Hindi, human translators did worse, and English German as well, human translators did worse than the machines. But for all the other languages, the human translators were better. So the main color coding that I want to highlight here is all the green things are large language models. There's some historical anachronism that the large language models, we can actually give them the names. So Command R+ and GPT-4, these are all the large language models that are out there, so they do pretty well. So the Tower large language model that I just mentioned also kind of does really well in lots of these language pairs. And the blue ones are commercial machine translation models. So there are things like Google Translate or Microsoft Live Translator or DeepL, and but for some reason we have to anonymize them. So there are, you don't necessarily know what they are. But that's kind of, we basically take kind of the leading state-of-the-art systems here and put them in. All the gray ones are actually the systems that this shared task is mainly targeted. These are all research systems. A lot of them also use large language models in some way or another. So, but then you have to look in detail how they do things. So these are all targeted. specifically built systems for this task. So we're definitely at the point where large language models are as good as, and maybe better, but not entirely clear than, you know, the Google Translates of the world. There are a few things that language models can also do that regular machine translation models can't do. So one is to give some examples before translation. Yes, we did explore that a bit in neural machine translation, but kind of the mainstream neural machine translation models don't really do that. Yeah, let me just quickly go over that. And another thing that they can do with large language models is to give them some specifications. So you can just say, translate that, but write it in the style of William Shakespeare, or translate that, but use formal language. Or translate that, but write it in the style of a marketing message, and so on. Or use the following terminology. So that's kind of a big issue. And in a professional translation world, that you often have like a style guide. You often have a terminology list that you have to follow. And it's very hard to get that into Google Translate. But with a large language model, you can just add that to the prompt and you can specify that. So if you don't have a style guide, but just have example text, you can also just provide example of the target language text in the expected style as part of the prompt. So these are things you couldn't really do with machine translation systems before, but you can now do with large language models. So here's the big caveat that these large language models are much more costly, at least in terms of computational costs. I recently went to a conference where they defined cost by how much you have to pay for the API, and apparently the API access for large language models is actually pretty cheap, but that might be just temporary because all this is heavily venture capital funded and subsidized. And if you actually go to the cost, which is how expensive is going to be the machine that is needed to run this model, how expensive is going to be the machine to train these models, and how expensive is the machine to kind of adapt this model to a particular use case, all that is massively more expensive for large language models. So I already mentioned the number of 1,000 times bigger large language models than the kind of transformer big models, but yeah, somewhere between 10 and 100,000 times bigger models are needed. They're much more expensive to use. Okay, next thing I want to talk a bit more about is, yeah, what does it mean for the translator today? So machine translation and the translator. So first of all, this is a bit of a discussion of where we are with the hype. So this is a long insight in the machine translation world that it went through various cycles where people made great claims, typically in the form of, it's going to be solved in 5 years. And then nothing got solved, and it was actually pretty terrible. And that was really bad for the field because nobody would fund our research anymore, and nobody was interested in it anymore, and nobody wanted to be associated with it anymore. So at least when I started research in this world, which was around the year 2000, we were rather cautious about not promising too much. Unfortunately, the field is now currently overrun by all the kind of AI startup companies, and they claim that, you know, artificial general intelligence is just around the corner. So the hype is definitely out of control, but the reality is also that things got better. I mean, machine translation is definitely much more usable than it was 5 years ago, 10 years ago, or 20 years ago. So here's kind of the hype headlines you can read, you know, artificial general intelligence is already here, or there was like this big story about Google engineer who was put on leave after saying that AI chatbot had become sentient, and users say that Microsoft's AI has alternative personality as godlike AGI that demands to be worshipped, and so on and so on and so on. You know, some AI inventors claiming, urging courts to recognize them as sentient. So I think reality for kind of all this large language model world is, I think they're very good as assistant systems. So that's the kind of uses that I'm mostly familiar with. So people use that a lot for kind of writing assistant, find grammar mistakes, rephrasing stuff, fleshing out outlines, or that's the thing I actually use them for a lot is as programming assistant. So previously, if I didn't quite remember the syntax for a command, I previously searched the web, found some web page on Stack Overflow that explained me how to do it. Now I can just ask a language model, and it gives me some suggestions. In both of these cases, you get some response from the large language model, and you're still the expert. So you can still figure out, did that actually make sense? So if you ask the language model to rewrite your sentence and then it completely changes the meaning, you notice that's not what I wanted. So you can reject it. So, and sometimes it gives you good ideas and then you use it. So you're still kind of the expert who uses the large language model as a system. And that's kind of very similar to the mantra we always had in machine translation, where we said, no, we're not going to solve translation. So it's not ever going to get solved. You're just going to build systems that are going to be good enough for various purposes. Maybe just initially, we just wanted to understand the general meaning of a document that's in a foreign language. So we get like a document with all kinds of weird foreign scribbles. We run it through our machine translation system. We now know, oh yeah, that's a sports report. Or it has to be good enough to be useful for travel communication. If you travel abroad and you don't speak the language of the country you're traveling in, kind of having a handheld device. It doesn't have to be perfect. It has to be enough. If there's some misunderstanding, you can rephrase your question or rephrase your sentences in various different ways. Or you can use other tools to communicate by pointing at things. So again, it doesn't have to be perfect in that. It just has to be good enough to be helpful. And then the final thing, obviously, is that it has to be good enough to serve as a draft for professional translators. So professional translators fast that I post-editing machine translation, or that fast that I translating from scratch. So that last point here, so this is kind of a very interesting chart from a fairly large translation company. So they employ a lot of professional translators. They use heavily machine translation. So they present translators with either fuzzy matches or with machine translation. And they measured over time how fast the translators are in translation when you present them with kind of a draft translation. And this has gone down from a bit over 3 seconds per word in 2015 to now about 2 seconds per word. And yeah, this is actually a chart from like 2 years ago. And then they kind of very suggestively draw a straight line there with dots and dots and dots. And at some point, it's going to intersect the line of 1 second. So that is, if it's a perfect translation, you still have to read it to check everything is okay. And then even if everything okay, then you just say, keep going. But you still had to read it. So 1 second per word is how much time you're going to need just to kind of verify that something is a perfect translation. And if you follow this dotted line, you kind of hit the intersection at 2027. Also has this great title of Singularity in AI. But whenever I press the author of this chart, they were a bit cagey, saying, no, we're not making predictions. But there's clearly progress that kind of really lines up, improvements in machine translation quality and improvements in productivity of translating. So we were very interested in the space a few years ago, where we built a tool called �H𝐬𝐧𝐞, where we thought maybe we don't want translators to just post-edit machine translation. Maybe we just want to basically build them a system that is a bit more like autocomplete, so that makes suggestions what the next word should be. So this is now fairly common in, like, if you write your email in Gmail, for instance, and you start your email message, it already gives you predictions how you should write. Or if you basically write a text message on a phone, same thing. You kind of it gives you suggestions what the words should be. So that was the idea. So the reason why this is going to be better than just writing your email is because it obviously knows the source sentence, so it has a pretty good idea what the translation should be. So it has a much better way of predicting what the next word should be. So by default, this would just feed you the machine translation word by word. But if you make any changes to it, it recomputes and comes up with new suggestions. To give you a bit of idea how this works, so this is here. Maybe an example. So you have a source sentence here in German. Er hat seit Monaten geplant, im März einen Vortrag in Singapur zu halten, and then it just makes suggestions as like, hey, you should translate the word he first. Produce the word he first. And then you can just accept that, and then it says, hey, produce the word plan first. Next. And then you say, yeah, sure, I'll go with that. And then it says like, you should produce the word for months next. And then you're like, oh, actually, I don't like that. I want to rewrite that. I want to say he has, and then it kind of recomputes and comes up with a new suggestion, says he has planned, and it keeps from there. A couple of other things we did in this tool that might be useful for a translator is if you have like some of the sentence translated, we kind of gray out the words in the source sentence that are already translated, so you don't need to look at them anymore because they're already covered. And when it makes now a suggestion of translated word next, you highlight the word in the source sentence, what this is a translation of, and white now what still needs to be translated. So that's kind of a nice feature. One idea we had but didn't really built into the tool was this idea that you have a translation and then you have this sentence and you're like, yeah, but I don't like this part in the middle here. So can you give me like alternative translations for that part in the middle? So we kind of played around with that, but during that project, we never really got a good satisfactory solution. So the idea was a bit that we need to paraphrase that, or we need to find alternative translations for that, and then also use a language model to figure out what fits in there kind of nicely. So that was kind of a nice feature we wanted to build at some point. Okay. Yeah, and the most ambitious thing that we didn't really get to at all was automatic reviewing. So if a human translates something, even if they're a professional translator and they pay good attention, they might still make mistakes. So the things that we thought we could spot automatically were things like, did anything get dropped during translation? You know, it's a very long sentence and you just forgot to translate it like a subclause or like some prepositional phrase. So,
Professor.
Yeah.
Sorry for stopping you. So this session tells me that it ends in 3 minutes or 2 minutes.
Okay.
So can we take it to another session?
Okay. So what should I be doing then?
So I sent you the link. So it's pinned in the comments. Check the comments, please.
So I'll click on that.
Yeah. There we go. Yeah. It's working. Yeah. Yep. That's good. Okay.